Welcome back to Swecodes. Today, we're going to untangle a neat little puzzle from Leetcode, minimum operations to make the integer 0. Open VS Code, get comfy, and let's walk through this together, slowly, clearly, and without any rush. What's the core idea? You're given two integers, num1 and num2. One move looks like this. Pick an I between 0 and 60 and subtract 2 to the power of I plus 1 num2 squared from num1. Your goal is to land exactly on 0 using as few moves as possible. If it can't be done, we return -1. That's it. Let me say it one more time in an even simpler way. Every move removes a bundle that's a power of 2 plus num2. We're choosing how many bundles to use and which powers so that the total subtraction is exactly num1. A quick word on constraints. Num1 can be as large as 1 billion. Num2 can be negative or positive, all the way to plus or minus 1 times 10 to the 9th power. And I, the exponent we choose, stays in the range 0 to 60. That last detail is a quiet gift. It means we'll never need to consider more than 60 moves. So whatever we do, our search can be tiny. Let's warm up with two examples. First one, num1 equals 3, num2 equals -2. Try I equals 2, so the bundle is 4 plus -2 equals 2. Subtract that, 3 becomes 1. Do the same again. 1 becomes -1. Now pick I equals 0:1 plus -2 equals -1. Subtracting -1 is the same as adding 1, so -1 becomes 0. We used 3 moves and that's optimal. Second one, num1 equals 5, num2 equals 5, 7. The smallest bundle is with I equals 0. 1 plus 7 equals 8. Subtract 8 from 5 and you're already below 0. And there isn't a way back because every bundle is at least 8. So here the answer is -1. Now for the trick that makes this problem pleasant. Imagine we decide up front we're going to use exactly k moves. What does that mean? It means we subtract num2 exactly k times, and we also subtract k powers of 2. If we shuffle terms a bit, we get a clean target. So for a fixed k, the question becomes, can the number be written as a sum of exactly k powers of 2? Repeats are allowed. Here's the lovely binary fact that unlocks it. Let b the number of ones in the binary representation of, that's the pop count. You need at least powers of 2 to build. Each 1 bit is a required coin. You're allowed to use more than because a larger power can always be split into 2 smaller ones. That gives us a simple feasibility rule. Why the part? Because even if every coin were the smallest power, k1s can only sum to k. So you can't make a value smaller than k with k coins. And because our exponent I can't exceed 60, it's enough to try k equals 1 up to 60. Tiny search, big payoff. Let's explore 3 approaches so you see the landscape. Approach 1, brute force sequences, for intuition, not for speed. You can imagine building a tree where each level is a move and each branch is a choice of I from 0 to 60. You'd search until you hit 0 or you reach 60 levels. That blows up fast. It's useful to picture what's going on, but we won't implement it to solve the problem. Approach 2, the clean one. Enumerate k, check the bit condition. This is where the math pays off. For each k from 1 to 60, 1, compute 2. If and then k works, return it. 3. If none works by 60, return -1. That's basically constant time, at most 60 quick checks, and constant space. Approach 3. Same as approach 2, but with small, friendly accelerations. 2 lightweight ideas. If there's no way k can work, so we can jump k forward to f of x directly, because the minimum coin count is the pop count. If num2 is positive and you ever see, x will only drop as k increases. Once you cross that line, k less than or equal to x can't be saved, so you can stop. The worst case is still the same tiny 60 checks, but in practice, it often finishes even earlier. Let's read the examples through this lens. For num1 equals 3, num2 equals -2. K equals 1. Pop count is 2. We'd need at least 2 coins. We only allowed 1. Not yet. Dash. K equals 2, pop count is 3. Still short. K equals 3. Pop count is 2. Now, so k equals 3 works. For num1 equals 5, num2 equals 7. K equals 3. 1 : negative. Can't be a sum of powers of 2. Since num2 is positive, increasing k will push x even lower, so we can safely give up. Answer, -1. Approach 2. Enumerate k equals 1 to 60 and check feasibility with pop count. Time, 060 tilde 01. Space, 01. We loop k from 1 to 60. We compute the leftover target x. If x is negative, we can't make it from powers of 2. If x is smaller than k, even using k1s won't reach x. Otherwise, we check the pop count rule. If the number of 1 bits in x is at most k, and k isn't bigger than x, we're done. Return k. A slightly snappier version. Approach 3 with the small jumps. Approach 3. Same feasibility check, plus jumping k to pop count x if needed. If you prefer no assignment expressions in Python, replace those lines with simple if-else and continue. Same logic. Quick recap so this sticks. We reframe the problem in terms of how many moves we're going to use. K. For a fixed k, the leftover target is. We can build from k powers of 2 if and only if and. Try k from 1 to 60. The first k that fits those inequalities is the answer. No fit? Return -1. It's fast, it's tidy, and it's easy to code safely. Complexity. We do up to 60 checks. Each check is a couple of arithmetic operations and a pop count. So time is essentially O of 1 for the given limits, and space is O of 1. Common gotchas. Use long in Java when computing x to avoid overflow. Don't try to build a -x from powers of 2. It's impossible. And remember both sides of the inequality. You need enough coins, that's pop count, but you also can't use more coins than the value you're trying to reach. That's the whole story. Once you see the pop count angle, the problem goes from yikes to, oh, okay. If this felt calm and helpful, that's exactly the Swecodes goal. Make the tricky things gentle. Nice work today. See you in the next one.